Hello and welcome friends to this video on chapter 1 on real numbers. This video contains everything that you need to know for the chapter 1 of NCERT textbook for the CBSE or ICSE boards, and in this video we cover everything from exercises, examples to theory, and all you need is to just watch this video. This video covers 1.1 Introduction, 1.2 Euclid's division lemma, Theorem 1.1 Euclid's division lemma. It also covers Euclid's division algorithm, all the exercises like exercise 1.1, exercise 1.2, exercise 1.3, exercise 1.4, and it also has a summary. To know everything about the chapter 1 on the real numbers, watch this complete video. But before you do that, you have to do a small thing. Please subscribe to our channel and like our videos. And also please feel free to share our videos and talk about our channel on the Facebook, WhatsApp, and other social media. This is a long video and it contains everything you need to know for the NCERT mathematics textbook for ICSE or CBSE board. In between there are messages like this one which request you to subscribe, share or like our channel. During those portions of the video you can take a break or you can skip those portions of the video. Also remember that you can get the links for the individual portions of this video from a playlist, and this playlist is given in the description of this video.
Mathematics for grade 10, real numbers. In this video, we shall learn the Euclid's division lemma and Euclid's division algorithm. These two things, namely Euclid's division lemma and Euclid's division algorithm, are very closely interlinked, so that many times people use these two things interchangeably. But what does Euclid's division lemma actually state? The division lemma by Euclid states that any positive integer a can be divided by another positive integer b in such a manner that it leaves a remainder r which is always smaller than b. Now let's state this Euclid's division lemma in a more formal manner in form of Theorem 1.1 of the textbook, which states that Euclid's division lemma is for a given positive integer a and b, there exist unique integers q and r which satisfy these two conditions, which are a is equal to b times q plus r, the remainder, and r is between 0 and 1, 0 and b, and r can be 0, that is 0 is less than or equal to r and r is less than b. Two things should be noted here, that both q or r can be 0. They can be 0 simultaneously as well. If both q and r are 0, then as per this equation a will be 0 as well. The other thing to note is that for a given a and b, the values of q and r are unique. That is, for the given a and b, the q and r are the only integers which satisfy the conditions a is equal to b times q plus r and 0 is less than or equal to r and r is less than b. In summary, we can say that r is greater than or equal to 0 and r is smaller than b is the Euclid's lemma. Before we go to the Euclid's division algorithm, let's try to differentiate between an algorithm and a lemma. Algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. Or in other words, algorithm can be a well-defined set of steps or procedures which yields an output or a result or solves a given problem. Lemma, on the other hand, is an already proven statement which is used for proving another statement. So lemma is a proved statement which is being used for proving something else. Now we go to Euclid's division algorithm. Note that this is algorithm here, so it will have some steps. So in case of Euclid's division algorithm, we have these steps. And what does Euclid's division algorithm state? It states that to get the HCF, the highest common factor, of any two positive integers, say c and D, where C is greater than D, we can follow these steps. Step 1 is apply Euclid's division lemma to C and D to find the whole numbers Q and R such that C is equal to D times Q plus R, and 0 is less than or equal to R and R is less than D. The step 2 is if the remainder is R is equal to 0, then D will be the HCF of C and D. But if R is not equal to 0, then we will apply the division lemma again to D and R. So these two are different. Earlier we applied the lemma to C and D, but now we shall apply them to D and R. So the step 3 will be, that is to continue the process until the remainder is 0, and that is when R is equal to 0, and then at that time when the R is equal to 0, the divisor at that time will be the required HCF. And just to refresh your memory, we can say that HCF of two positive integers a and b is the largest meaning the highest, and the word h in HCF is highest. So the largest positive integer d that divides both a and d. So HCF of two numbers a and b is the highest integer d which divides both a and b. Now let's do some examples. This is example 1 from the textbook, and it asks us that use the Euclid's algorithm to find the HCF of 4052 and 12576. So let's take the first steps to solve this, and we notice that 12576 is bigger than 4052. So we shall keep this 12576 in the dividend position, and let's apply the lemma to these two numbers, and we obtain an equation like this. So we have 12576 is equal to 4052 times 3 plus 420. So we notice that this equation has remainder of 420, and this remainder of 420 is not equal to 0, so we shall continue to apply the lemma again. And when we apply lemma, now the numbers will change. The 420, which is a remainder here, will become the divisor here, and 4052, which is the divisor here, will become the divisor, 4052 will become the dividend here. So we apply the lemma again, we get the remainder 272. So the remainder 272 is still not 0, so we shall apply the lemma again to the numbers 420 and 272. 272 comes from here, this was the remainder, 420 is the divisor, and current divisor 420 will become the dividend here, and the remainder for 272 will be the divider, the new divider. When we do this, we get a remainder of 148. This 148 is still not 0, so we apply the lemma again. We get the remainder 124. Divisor here is 148, but the remainder is still not 0, so we apply it again, and we get the equation 148 is equal to 124 times 1 plus 24. 24 is the remainder, which is still not 0. So let's continue this process once again. So we get 124 is equal to 24 times 5 plus 4. So the remainder is 4, which is still not 0. So let's apply the lemma once again. So we get 24 is equal to 4 times 6 plus 0. So now you see this time the remainder is 0, and therefore our procedure will stop. Now you see the divisor in this last equation is 4, and this 4 by the algorithm by Euclid we will say will be the HCF of 12576 and 4058. You will notice that the 4 is HCF of other pairs in these equations as well. And let me change the ink color to highlight that 4 will be the HCF of 24 and 4, which is, if you see here, 24 and 4. 4 will also be the HCF of 124 and 24, which is 124 and 24. 4 will also be the HCF of 148 and 124, which is 148 and 124, and so on. So if you see in all the combinations of C and D above in the form here, like 272 and 148, 4 will be their HCF as well. So we have solved this example and we have found the HCF of 12,576 and 4,052 as the number 4. Let's now get to the example number 2, which is to show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1, where q is some integer. So to start solving it, let us assume a to be any positive integer and let b is equal to 2. Now using Euclid's lemma, we can write a as equal to 2 times q plus r. So if you notice in our case, b is 2 and we have a is equal to b times q plus r. And in this case, q is some integer greater than 0. So we have taken q to be basically greater than or equal to 0. And r is the remainder, is some integer which is greater than or equal to 0 and is less than 2. That is, r is either equal to 0 or r is equal to 1. Because as per lemma, the r will have to be smaller than the number 2. So we have this r as either equal to 0 or this r is equal to 1. So when this r is equal to 0, we have a becoming equal to 2q, and when then r is equal to 1, in here we get a is equal to 2q plus 1, because we put the value of r is equal to 1 here, so we get 2q plus 1, which is nothing but a is equal to 2q plus 1, and when r is equal to 0, we put r is equal to 0 here and we get this value as a is equal to 2q. So if a is of the form 2q, then a is an even integer, because any even integer is divisible by 2 and this is divisible by 2. Similarly, we can say a positive integer can be either even or odd, so we have any positive odd integer is of the form 2q plus 1. So we have solved this example as well. Let's go to the third example, which is show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. So let's suppose a is a positive and also an odd integer. We apply Euclid's division algorithm with the a and the number 4, and the equation will look like this. A is equal to 4 times q plus r. Now the lemma states that the remainder r has to be between 4 and 0, that is 0 is less than or equal to r and r is less than 4. So this implies that the values that r, the remainder, can get is either 0 or 1 or 2 or 3. So now let's place all these values of r into our equation here. Okay, so we can get a will be equal to 4q when r is equal to 0. Similarly, a will be equal to 4q plus 1 if r is equal to 1. Similarly, when r is equal to 2, the value of a will be 4q plus 2. When r is equal to 3, value of a, that is this, will be 4q plus 3. Now we have already assumed that a is an odd number. We had assumed it here to be an odd integer. So we can say that our well a cannot be 4q or 4q plus 2, because both these 4q plus 2 and q can be divided by 2. So we basically can easily rule out equation 1. So this equation 1 is ruled out, and similarly equation number 3 is basically ruled out. So a cannot be this and a cannot be this. So we are left with that a, which is an odd integer, is either equal to 4q plus 1, which is this, or it is equal to 4q plus 3, which is this. And hence we have solved what is asked of us in this example number 3. Let's do one more example, and this will be the last in our video. Example 4 is from the textbook. It states, a sweet seller has 420 kaju barfis, which is a kind of a sweet, and she also has 130 badam barfis, a different kind of sweet. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. So we have to find out what is the number of the barfis, that is those sweets, that can be placed in each stack for this purpose. In lower grades or classes, we would have solved this problem by trial and error method, but in this case we will solve the problem more systematically, that is by finding the HCF of the given two numbers 420 and 130. So if we find the HCF of these two numbers, we shall get our answer, because that will be the number that we can stack, number of barfis that we can stack when the area of the tray used will be the least. So our problem is to solve and get the HCF of 420 and 130. The first step is 420, which is the bigger number, we keep it on the left hand side, and the 130, which is the other number, is the divisor, multiply by 3, and we get 30 as the remainder, r. So this r30 is not 0, so we continue to the next step, and the next step is we move the divisor to the dividend position. 130 is here, is equal to 30 is the remainder from the previous step, and we get 10 as a remainder in this step. This 10 is again not 0, so we will have to solve this one more step at least. So we place 30 here, 10 the previous remainder here, and 3 is the multiplier this time, and 0 is the remainder this time. So now that we have hit 0, the divisor in our case is 10, will be the HCF, and hence the answer. So HCF of 420 and 130 is 10, and we can say that the sweet seller can make the stack of 10 of both kinds of barfis, and that is the answer for our example number 4.
Hi, in this session we shall talk about the question number 1 in exercise 1.1 of chapter 1 on real numbers for grade 10, class 10th. The question number 1 says we have to use Euclid's division algorithm to find HCF of 135, 225, 196, 38,222, 20, and 867 and 255. Now the answer to the first part is that we have to find the HCF of 135 and 225. We notice that 225 is greater than 135. So when we are using the Euclid's lemma or Euclid's division algorithm, we shall keep the bigger number in this position on the left hand side, which is the dividends position, and the smaller number will take up the position on the right hand side as that of a divisor, that is 135 in our situation here. So we take the first step and we see that 225 is equal to 135 times 1 plus 90. So at this stage the remainder is 90, which is not equal to 0. So we shall apply the lemma once again, but this time the lemma will be applied onto 135, which was the divisor in previous stage, and it will become a dividend here, 135 on the left hand side, and the remainder from last time goes onto the divisor's position. So we get 135 is equal to 90 times 1 plus 45. Again 45 is the remainder, which is not 0, so we carry on this step once more.
So we get 90 is equal to 45 times 2, and the remainder in this case is 0. So now that we have reached the stage that the remainder is 0, so the process will have to stop, and at this stage the divisor is 45, and therefore the HCF of 225 and 135 will be 45, and this is our answer. Let's get to the part number 2, where we shall find the HCF of 196 and 38,220. So to find the HCF, we notice that 38,220 is a bigger number, so we keep it on the left hand side here, and the smaller number 196 is placed on the right hand side in the divisor position, and we see the equation 196 multiplied by 195 plus 0 is equal to 38,220. So we have reached the stage where the remainder is 0, so we shall stop the process, and the divisor at this stage is 196, so HCF of these two numbers will be 196, and we can say our answer is 196. Let's get to the next part 3 of this question number 1, which is to find the HCF of 867 and 255. As usual, the bigger number 867 is kept on the left hand side, 255 goes in the position of a divisor, and we carry on we apply the Euclid's lemma, and we obtain a remainder of 102. 102 is not equal to 0, so the process will continue, and this time we apply the process with 255 in the left hand side as the dividend, and 102 remainder from the previous step will be in the divisor's position. Still the remainder is 51, which is not equal to 0, so we carry on this step once more. 102 reaches to the left hand side, 51 times 2 plus 0. So this time we have reached the stage where the process has to end, and we can say that the HCF of 867 and 255 is 51. So the 51 as a HCF is our answer.
In this session, we shall do questions 2 and 3 of exercise 1.1. This is mathematics on real numbers for grade 10. The question number 2 says, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. We shall solve this problem by using Euclid's lemma, and let's start. Let's say a is a positive integer, and using the lemma we can express a as equal to 6q plus r, where r is between 0 and 1 and r can take value equal to 0, and q is greater than or equal to 0. Since we have r is between 0 and 6 and it can take value 0, the r can take value 0, 1, 2, 3 and 4 and 5. If we write them here, let's say when r is equal to 0, we have a taking value as 6q. When r is equal to 1, it takes value 6q plus 1 and so on. When r is equal to 5, then a is equal to 6q plus 5. Now let's see, in the question we are asked to about these forms, 6q plus 1, then we asked 6q plus 3, then we are asked 6q plus 5. So let's expand further these items, like 6q plus 1. Let's expand it further, and we can see that it is equal to 2 times 3q plus 1. And if we decompose it further, we can say that it is 2 times c1 plus 1, where c1 is a positive integer which is equal to 3q. Similarly, let's focus on the other 6q plus 3 form,
decomposing it further, we get A is equal to 2 times 3q plus 1 and then plus 1, which again is of a form 2 times c2 plus 1, where c2 is a positive integer equal to 3q plus 1. Then similarly, let's focus on to the next form, 6q plus 5. We are focusing on them because they are asked in the question, and we can ignore, or there is no need to decompose or analyze further the forms where a is equal to 6q or a is equal to 6q plus 2. So if we decompose the form 6q plus 5, we see it is equal to 2 times 3q plus 2 plus 1, which is of the form 2 times c3 plus 1, where c3 is a positive integer equal to 3q plus 2. Now if you see that all these forms 6q plus 1, 6q plus 3 and 6q plus 5 are of the form 2 times c plus 1, where c is an integer. So if you see, this is 2c plus 1, this is also 2c plus 1, 2c plus 1, 2c plus 1. So we can see that a is taking form of 2c plus 1. Now if you notice carefully, 2c plus 1 is not exactly divisible by 2, because this is divisible by 2, but then if you add 1, then it is not divisible by 2, meaning exactly not divisible by 2. So we can say that these are the expressions of odd numbers. So basically, when a is of the form 6q plus 5, it is an odd number, and therefore we can easily say that any odd integer can be expressed in the form 6q plus 1 or 6q plus 3 or 6q plus 5, as it has been asked in the question. So we have solved this question, and let's get to the next question. Our next question is question number 3, which asks, an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. Then we have to find out what is the maximum number of columns in which they can march. So as we have to find the maximum number of the columns of the 616 members of the army contingent and the 32 members of the band, it can be found out by simply finding the HCF of these two numbers, 616 and 32. So let's use Euclid's algorithm and find the HCF. We are keeping 616, that is 616, on the left hand side because it is bigger than 32, which is in the right hand side in the divisor position. On a step 1, we see 616 is equal to 32 times 19 plus 8. 8 is the remainder here, and this is not equal to 0. So we continue the step further, and we get 32 is equal to 8 times 4 plus 0. 0 is the remainder, so we stop the process and we get the HCF as in this case of 8. So HCF of 616 and 32 is 8. And 8 is the column number, and it is our answer. But if we were to visualize this, how shall these columns of army band and the army contingent look like? Let's see it in this picture. So we found out that there were 8 columns. So if you count, then these are the 8 columns: column 1, 2, and 3. So one column is of this length, so 77 members of the army contingent, and then the 4 members in each column for the army band. So in this case, as if the entire contingent and the band are marching from left to right, maybe let's say in the west to east direction, but we can draw the columns in up and down fashion, that is north and south as well, something like this also. So again, the number of columns is 1, 2, 3, 4, 5, and it is up to 8. And there are 77 army contingent people in one column. Hi, this session is for questions 4 and 5 of exercise 1.1 of chapter 1 on real numbers for grade 10. Let's solve question number 4, which says use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So to solve this, let's assume a to be any positive integer, and then using Euclid's lemma, a can be expressed in terms of q and r such that a is equal to 3q plus r, where q is greater than or equal to 0 and 0 is less than or equal to r and r is less than 3. So if this is the expression for r, then r can take values 0, 1 or 2. And in each of that situation, when r is equal to 0, let's see what is the value of a. So when r is equal to 0, a will be equal to 3q. When r is equal to 1, a will be 3q plus 1. And when r is equal to 2, a will be equal to 3q plus 2. And now just keep it in your mind that in the question we are asked positive integer, and then we are asked, or we are told, or there is a mention of forms 3m or 3m plus 1 in the question. So let's see what happens to a square, and if we can decompose a square into either form of 3m or of the form 3m plus 1. So let's try writing a square when r is equal to 0. So when r is equal to 0, a square will be equal to 3q whole square, which will be equal to 3 times 3q square. Similarly, when r is equal to 1, a square will be of the form 3 times 3q square plus 2q plus 1. And when r is equal to 2, a square can be written into the form of 3 times 3q square plus 4q plus 1 plus 1. And in summary, it is that a square is equal to 3 times 3q square, which is equal to, or which can be summarized in the form 3c1, where c1 is equal to this 3q square. And similarly, when we have r is equal to 1, a square will be of the form 3c2 plus 1. When a square, the form a square will take when r is equal to 2 will be of the form 3c3 plus 1. And if you see closely, these two are of the same form, which is same as 3m, and this is of the form 3m. Hence we can say that the square of a positive integer is of the form 3m or 3m plus 1, and hence we have solved the question. Now at question number 5, which is use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. So we shall show this by first assuming let a be any positive integer, and then using Euclid's lemma, a can be expressed in terms of q and r such that a is equal to 3q plus r, where q is greater than or equal to 0 and r is greater than or equal to 0 and r is less than 3. So this implies that r can take values which are 0, 1 or 2. So we have three, let's say, scenarios where r is taking different values. So let's start with first value where r is equal to 0, that is a will be in this situation equal to 3q, and then the a cube will be 3q whole cube, which will be equal to 27 times q cube, which is equal to 9 times whole cube of 3q, and which can be expressed as equal to 9m, where m is an integer such that m is equal to 3q cube. Now let's go to the next scenario where r is equal to 1, that is a is equal to 3q plus 1, because if you put r is equal to 1 in the top equation here, where a is equal to 3q plus 1, you will notice that when r is equal to 1, it will take shape a is equal to 3q plus 1, then a cube will be 3q plus 1 whole cube, and it can be further decomposed and shown in the format 9 times 3q cube plus 3q square plus q plus 1, which is of the form 9m plus 1, where m is equal to 9 times 3q cube plus 3q square plus q. You notice here that we are given in question these forms 9m, 9m plus 1, 9m plus 8. So our attempt is to get these forms somewhat similar to them. So when we achieved, let's say, this form or this form, we should keep in mind the target that we are trying to express it into a form of 9m plus 1. So let's go to the third scenario where r is equal to 2, and in that situation a will be equal to 3q plus 2, then a cube will be 3q plus 2 whole cube, and this can be further decomposed and shown in the form of 9 times 3q cube plus 6q square plus 4q plus 8, which is equal to 9m plus 8. And if you look carefully, this is of the form that is asked or mentioned in the question. So we have achieved that form where m is 9 times 3q cube plus 6q square plus 4q. So what we have here is that from these three cases above, the case this one, and this one, it is proved that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. Hence we have solved this question number 5. Hi, in this session we shall deal with the Fundamental Theorem of Arithmetic. This session is for grade 10 on real numbers. Before we go to the Fundamental Theorem of Arithmetic, let's revise what a prime number is and what are the composite numbers. A prime number is a natural number meaning the counting numbers like 1, 2, 3, like that. And we can say a prime number is a natural number greater than 1 that cannot be formed by multiplying two other natural numbers. In other words, we can say that a prime number is a natural number which is divisible by two natural numbers, and those two natural numbers are 1 and the number itself. So the point to note here is that it is divisible by only two and exactly two numbers, and those two numbers are number 1 and the number itself. And what are the composite numbers? A composite number is a natural number which is greater than 1 and which is not a prime number. Then that number is called as a composite number. So we have seen a prime number, and the number which is not a prime number is a composite number. And what about the number 1? We know by these definitions, because you see the prime number is greater than 1 and a natural number greater than 1 can be a composite number. We notice that 1 is neither a prime number nor a composite number. Okay, so now let's talk about the Fundamental Theorem of Arithmetic. The basic idea of this Fundamental Theorem of Arithmetic is that any integer above 1, meaning greater than 1, is either a prime number or it can be made by multiplying the prime numbers together in a unique manner. So the unique manner will be there if we ignore the order. So let's say 2 multiplied by 3, and it can be 3 multiplied by 2 as well. So we shall have to ignore the ordering of them. Let's say let's take some examples. Let's say we have numbers 2, 3, 4, 5, 6 like that we have here, up to 14, and then there could be many more, and let's say there is an in between number 32,760 and so on. So number 2 is a prime number, number 3 is a prime number, number 4 is a composite number, number 5 is again prime, 6 is composite, 7 prime, 8, 9, 10 are composites like that. So let's see if we consider let's say a composite number 4, and from the basic idea here we notice that the composite number can be formed by multiplying the prime numbers. So number 4 is formed by the multiplication of number 2, which is a prime number. So 4 is equal to 2 raised to power 2. Similarly, let's take another let's say composite number 2, which is composite number 10, which is formed by multiplication of 2 and 5. So again 2 and 5 are the prime numbers, and a composite number is formed by multiplication of two prime numbers. In fact, as this basic idea says, that every composite number can be written as a product of powers of prime numbers. So it could be, let's say another example could be the 12, which can be written in the form of powers of 2 raised to power 2 multiplied by 3. So the basic idea is saying that any composite number can be formed by multiplication of prime numbers, and the prime numbers, they will be unique to obtain that given composite number. So now let's move on to our fundamental theorem of arithmetic. This is the theorem 1.2 in the textbook, and it states that every composite number can be expressed, that is factorized, as a product of prime numbers, and this factorization is unique apart from the order in which the prime factors are arranged or they occur. So basically it can be stated in the other words as well. So we can say that the theorem states that any composite number, meaning any number from let's say you can think of, can, and it is, if it is a composite number, it can be factorized as a product of prime numbers in a unique way, and unique way will be by ignoring the order in which the primes occur. So let's take example of number 12. This can be decomposed into 2 multiplied by 2 multiplied by 3, which is 2 raised to power 2 multiplied by 3. So this 2 raised to power 2 multiplied by 3 is unique. So the prime factors are 2 and 3. You cannot have any other manner in which you can obtain number 12 by having prime numbers on this side. You cannot obtain it. There is only one unique way that you can obtain number 2. So let's see it in some other words again. So this theorem can be expressed in some other words by saying that any composite number, for any given composite number, there is one and only one way to write this composite number as a product of prime numbers. So as long as we are not particular about the order in which the prime numbers are arranged. So what it states is that by ignoring the ordering of the prime numbers, we can obtain any composite number in a unique manner by unique prime factors. Let's talk about the same theorem in some more different words here. So the other way to state is that the prime factorization of a natural number is unique except for the order of its factors. So let's take example of 32,760. It can be expressed as 2 multiplied by 2 multiplied by 2 multiplied by 3 times 3 times 5 times 7 times 13, which is equal to 2 raised to power 3 into 3 raised to power 2 into 5 into 7 into 13. And if you see here, 2 is a prime number, 3 is a prime number, 5, 7 and 13 are prime numbers. So we have expressed 32,760 into its prime factors on this side. and this way is always unique. So what it is saying is that this is the only way to factorize 32,760 using prime numbers. There is one more point that we should remember when we talk about the fundamental theorem of arithmetic. So let's say in general, for a composite number c, we factorize it as c is equal to p times p1 into p2 into p3 into p4 and up to pn. So a composite number c is p1 times p2 times p3 times p4 up to pn, where the p1, 2, 3 and pn are the prime numbers which are written in the increasing order. This increasing order or the ascending order is important, and it can be expressed mathematically as p1 is less than or equal to p2 is less than or equal to p3 is less than or equal to p4 and all the way up to pn. So this increasing or the ascending order is important. So if we agree on arranging all the prime factors in increasing or let's say ascending order, then the prime factorization that we shall obtain for any number will be unique. So let's take example again of 32,760. So if this is expressed in its prime factors and the prime factors are increased in increasing order, either equal to or less than this format, p1 is less than or equal to p2 and p2 is less than or equal to p3, just like see here, all the 2's are first, then there are 3 and 5, 7 and 13. So this manner or this factorization will be unique, and that is what the theorem, the fundamental theorem of arithmetic states. Hi, in this session we cover mathematics, chapter 1 on real numbers for class 10th, and the section is 1.3, the fundamental theorem of arithmetic. We shall cover examples 5 and 6. Example 5 says, consider the numbers 4 raised to power n, where n is a natural number, and check whether there is any value of n for which 4 raised to power n ends in a digit 0. And the answer is, if the numbers 4 raised to power n were to end in the digit 0, then they would be divisible by 10. This is something we already know. For example, let's say any number which is ending, let's say 20, 30, they all end in digit 0 and they are divisible by 10. But we also know that 10 is a composite number which can be factorized as 2 multiplied by 5, which are its prime factors. So it means that 4 raised to power n, if it were to end with a digit 0, then it would be divisible by numbers 2 and 5. So in our case, let's talk only about the number 5. That is, the number 4 raised to power n would be divisible by 5, and if this is true, that is 4 raised to power n is ending in a digit 0, then the prime factors of 4 raised to power n would contain the prime number 5. That is, prime number 5 would be one of the prime factors of 4 raised to power n, and let's call this as our statement number 1. Now we also know that 4 raised to power n is equal to 2 multiplied by 2 whole raised to power n, and which is equal to 2 raised to power 2n, which implies that the prime factors of 2 raised to power n are 2 and only 2. So this is because the fundamental theorem of arithmetic says that the prime factors of a composite number are unique. So now let's call this as our statement number 2. So statement number 1 says that the prime factors of 4 raised to power n contains 5, but the statement 2 says prime factors of 4 raised to power n contains only 2. Now these two statements cannot be true simultaneously, so together they are not possible. Hence we can say that there are no natural numbers for them. There is no natural number n such that 4 raised to power n ends with a digit 0. Let's now talk about example number 5, which says find the LCM and HCF of 6 and 20 by the prime factorization method. we know that HCF of numbers is equal to the product of the smallest power of each of the common prime factor in those numbers, and the LCM of numbers is equal to the product of the greatest power of each of the prime factors involved in the numbers. So if you see these two sections up to here, the difference between HCF and LCM is the smallest and the greatest, and the remaining portion is a bit different. These are the common primes and the prime factors involved in the number. But let's get to solving and finding the HCF and LCM of numbers 6 and 20. If we factorize 6, it is equal to 2 raised to power 1 multiplied by 3 raised to power 1, and 20 is equal to 2 raised to power 2 multiplied by 5 raised to power 1. Hence the HCF, which is the smallest power of every common prime factor. So if you see, 20 has factors 2 and 5, 6 has 2 and 3. So what is common? 3 is not common, 5 is not common, so only common factor is 2. And what is the smallest power of this? Here the power is 2, here the power is 1, so the smallest power is 2 raised to power 1. Hence our HCF would be 2 raised to power 1. LCM on the other hand is the greatest power of every prime factor. So we have prime factor 5 involved here, we have prime factor 3 involved here, we have prime factor 2 involved here. So let's pick the greatest power of 5, we take it here, greatest power of 3, we take it here, and out of these two, which is the greater power? 2 raised to power 2. So let's take 2 raised to power 2 here, and hence the LCM of 6 and 20 is equal to 2 raised to power 2 multiplied by 3 raised to power 1 multiplied by 5 raised to power 1, which is equal to 60. Hence our answer is 2 and 60, where 2 is the HCF of the number and LCM is the 60. Hi, this is a session on mathematics, chapter 1 on real numbers for grade 10, examples 7 and 8 of section 1.3 Fundamental Theorem of Arithmetic. Example 7. It says find the HCF of 96 and 404 by the prime factorization method. Hence find their LCM. We have to remember that if A and B are two positive integers, then HCF of A and B multiplied by the LCM of A and B will be equal to the product of A and B. That is, for given two numbers, their HCF multiplied by their LCM is equal to their product. So now let's see, we are given two numbers 96 and 404. So to make our life easier, let's first take 96 and create some factors of it. In our case it is 32 multiplied by 3, and now let's further decompose them to get the prime factors of 96. So we decompose it further and we get 2 raised to power 5 and 3. These are prime numbers, and this is the prime factorization of 96. Similarly, 404, we decomposed it into 101 multiplied by 4, but we decompose it further into the prime factorization of 404. We get 2 raised to power 2 and 1 raised to 101. Hence the HCF of 96 and 404 will be the 2 raised to power 2, which is 4, because HCF is the smallest power of every common prime factor, and the common prime factor between this and this is only 2, and we take the smallest power, which is 2 raised to power 2, that is HCF of these two numbers, that is 96 and 404, is 4. Now we also know that LCM multiplied by HCF is equal to the product of two numbers. Hence LCM of 96 and 404 will be product of the two numbers divided by the HCF, which is equal to 96 multiplied by 404 divided by 4, which is 96, which is 9696. This is our answer. Let's take example number 8 now. we have to find the HCF and LCM of 6, 72, 120 using the prime factorization method. And let's recall the definitions of HCF and LCM. HCF is the product of the smallest power of each common prime factor in the numbers, and the LCM is the product of the greatest power of each prime factor involved in the numbers. So now let's carry out the prime factorization of 6, which is equal to 2 raised to power 1 multiplied by 3 raised to power 1. 72 can be factorized into its primes by 2 raised to power 3 multiplied by 3 raised to power 2, and then 120 will go into 2 raised to power 3, 3 raised to power 1, and 5 raised to power 1. So the HCF of these three numbers here will be 2 raised to power 1 multiplied by 3 raised to power 1, which is equal to 6. Similarly, LCM of the three numbers will be 2 raised to power 3, 3 raised to power 2, 5 raised to power 1, which is equal to 360, because as per the definition, if you see, we have to take the highest powers of the prime factors 2, 3 and 5 in this case, because the prime factors are 5, 3, 2, 5, 3 and 2, 3 and 2. So all the prime factors involved are 2, 3 and 5, and we take their highest powers to get the LCM. So we have found the LCM to be 360, HCF to be 6. So this completes our answer to this question number 8. But you see, we have talked about, in this session itself, we have talked about the HCF of two numbers multiplied by the LCM of two numbers is equal to product of the two numbers. But this thing does not apply to the three numbers situation. So if there are three numbers A, B and C, then the HCF of the three numbers multiplied by their LCM, that is LCM of A, B and C, will not be equal to the multiplication of A, B and C, that is product of A, B and C. And here we can check this in our example, because we are given three numbers 6, 72 and 120. If we multiply 6, 72 and 120, we get 51,840, and if we multiply the HCF and LCM of these three numbers, we get 2,160. Both are not equal to each other, and hence we can say that for the three numbers, their LCM multiplied by their HCF is not equal to their product. So for the three numbers, we can say that. Hi, this is session on mathematics, chapter 1, real numbers, for grade 10, exercise 1.2's question number 1. The question number 1 says, express each number as product of its prime factors, and the numbers are 140, 156, 3825, 5005, 7429. So the first is 140. We decompose into any factors. Let's say 2 multiplied by 35 multiplied by 2, and then we see the prime factors of it will be 2 multiplied by 2 multiplied by 5 multiplied by 7, and hence the product of its prime factors would be 2 raised to power 2 multiplied by 5 multiplied by 7. Similarly, let's do the second part, which is 156, and this can be decomposed as 4 multiplied by 3 multiplied by 13, and if we want to further decompose it into the primes, then it will be 2 multiplied by 2 multiplied by 3 multiplied by 13, which will give 2 raised to power 2 multiplied by 3 multiplied by 13, and this will be the product of the product of its prime factors. The part 3, 3825, this will be 9 multiplied by 25 multiplied by 17, and it can be decomposed further into the product of its primes as 3 raised to power 2, 5 raised to power 2 multiplied by 17. Part 4 is 5005, can be decomposed into 35 multiplied by 11 multiplied by 13, and the primes would be, and their product would be 5 multiplied by 7 multiplied by 11 multiplied by 13, and this will be the answer in this case. And the last part is the fifth part, which is 7429. It can be decomposed into 17 multiplied by 19 multiplied by 23, and the prime factorization would be 17 multiplied by 19 multiplied by 23, which will be same as the product of its primes, 17 times 19 times 23. Now if you see, the product of the primes is what we have found out here. This is our answer, and this is what we should be writing as a solution to this question. But you also note that we have written all these factors in the ascending or increasing order, because that's what the convention is. So if you see here, 17 is less than 19, which is less than 23. So there is an increasing or the ascending order. And let's take this third part. 3 is smaller than 5, which is smaller than 17. So again, this has been written in the ascending order. So this is what we should always write. So we should follow the convention that the factors are to be written in the increasing order. Hi, this session is on mathematics, chapter 1 on real numbers for grade 10. And the exercise is 1.2. The question number is 2. The question number 2 says, find the LCM and HCF of the following pairs of integers and verify that the LCM multiplied by the HCF is equal to the product of the two numbers. The part 1 is 26 and 91, and we shall solve this in this scenario now. We are given two numbers, 26 and 91, and if we see, the product of their primes would be 2 and 13 for 26 and 7 multiplied by 13 for 91. So if we go with the LCM and HCF of 26 and 91, we try to find them. The detailed process of finding out the LCM and HCF is given in the previous sessions of this series. And if we go by that method, we see that the HCF of 26 and 91 is equal to 13. And the LCM of 26 and 91 is equal to 2 multiplied by 7 multiplied by 13, which is equal to 182. So by this we have found out the HCF and the LCM. If this is the LCM, this is the HCF of the given two numbers, 26 and 91. And now let's do the verification part. What it says is that we have to verify that the product of the given two numbers is equal to the multiplication of the LCM and HCF of those two numbers. So let's see what is the product of the given two numbers. That will be 26 multiplied by 91, which is equal to 2366. And now let's try to find out the HCF multiplied by the LCM. LCM is here, and HCF, we will get 182 multiplied by 13. So you see, this 13 is the HCF and this 182 is the LCM. So their product will be 2366. So both these things are equal. So what it says is that the product of the given two numbers, which is 2366, is equal to the product of the LCM and HCF, 2366. So hence we can say that we have verified that the LCM and the HCF of the product of two numbers is equal to let me repeat. LCM and HCF when multiplied give the product of the two numbers. Let's do the part 2 of the question number 2. The given two numbers are 510 and 92. Let's factorize them. So 510 is 2 multiplied by 3 multiplied by 5 multiplied by 17, and the number 92 is equal to 2 multiplied by 2 multiplied by 23. So after having factorized them, we can find HCF and LCM very easily. So HCF for 92 and 510 will be 2, and the LCM for the two numbers will be 2 multiplied by 2 multiplied by 3 multiplied by 5 multiplied by 17 multiplied by 23, which will be equal to 23,460. So this we have found out the HCF and LCM. But now let's do the verification. So in our case, the product of the given two numbers is 92 multiplied by 510, which is equal to 46,920. And if we find the LCM multiplied by HCF, we will get 23,460 multiplied by 2, which gives us the same value, that is 46,920. So we see that these two things are equal. Hence we can say that we have verified that LCM when multiplied by HCF gives the product of the two numbers. Now let's get to the part 3, which is the two numbers given to us are 336 and 54. Let's try to find their HCF and LCMs. So if we factorize 336, we get 2, 2, 2, 2, 3 and 7. That is equal to 2 raised to the power 4 multiplied by 3 multiplied by 7. And the 54 in that case gives us 2 multiplied by 3 raised to power 3. So we can say that the HCF and the LCM, we have covered the detailed method or the procedure for finding out the HCF and LCM in our previous sessions. So we can say that the HCF is equal to 2 multiplied by 3 that is equal to 6. And LCM of 54 and 336 will be equal to 2 raised to power 4 multiplied by 3 raised to power 3 multiplied by 7, which is equal to 3024. So this way we have found out what was asked in the question. So LCM and HCF has been found out. But now let's do the verification part. So we see that the two numbers given to us are 54 and 336. Their multiplication when done, we get 18,144. And if we were to multiply the HCF and the LCM of the two numbers, we will get again 18,144. So these two numbers are same. So we can say that we have verified that the LCM when multiplied by the HCF gives us the product of the two numbers. Hi, this is a session on mathematics, chapter 1 on real numbers for grade 10, exercise 1.2, question number 3. Question number 3 says, find the LCM and HCF of the following integers by applying the prime factorization method. So let's solve the part number 1 first, which is that the given numbers are 12, 15 and 21. So if we factorize them, we get 12 is equal to 2 multiplied by 2 multiplied by 3, which is equal to 2 raised to power 2 multiplied by 3 raised to power 1. 15 would be decomposed as 3 multiplied by 5, which will be equal to 3 multiplied by 5. Similarly, 21 when factorized into its primes will give 3 into 7. So if we see this now, we can find HCF and LCMs very easily. HCF is the product of the smallest power of each of the common prime factor in the numbers. So if we see the common prime factors which are there, in this case we have 3 and we also have 2. In this case we have 3 and we have 5. In case of 21 we have 3 and 7. So the only factor which is common is 3. So we will get 3 and its smallest power will be 3 raised to power 1. So we get 3 here as the HCF. Okay, so let's get to the LCM, which will be the product of the greatest power of each prime factor involved in the number. So in our case, this will be 2 raised to power 2 multiplied by 3 multiplied by 5 and multiplied by 7, which will give us 420. Therefore, we have the LCM equal to 420 and the HCF of the three numbers is equal to 3. Let's get to the part number 2, third question and the part 2. The given numbers are 17, 23 and 29. If we do their factorization, we get basically 17 equal to 1 multiplied by 17, 23 is equal to 1 multiplied by 23 and 29 is only 1 multiplied by 29. So now we can easily find their HCF. So in case of HCF of the three numbers, we will check the smallest power of each of the common factor. And here we have only 1 as the common factor. So the HCF would be 1. In case of LCM, the product of the greatest power of each of the prime factor involved will be multiplied. So we get 17 multiplied by 23 multiplied by 29. So that will be 11339. So we have gotten the two numbers. We have gotten the HCF as 1 and the LCM of the given three numbers will be 11,339. Now let's do the last part of the question number 3, which is we are given the three numbers as 8, 9 and 25. And if we factorize them, 8 will become 2 raised to power 3, 9 will become 2 raised to power 2 and 25 will become 5 raised to power 2. And now let's do the HCF and LCM. So HCF of the three numbers will be 1 because that is the smallest power of each of the common prime factor. The LCM of the numbers 8, 9 and 25 will be 2 raised to power 2 multiplied by 3 raised to power 2 multiplied by 5 raised to power 2, that is 1800. This session is on Mathematics, Chapter 1 on Real Numbers for Grade 10, Exercise 1.2, question numbers 4 and 5. Question number 4 says, given the HCF of 306 and 657 is equal to 9, find the LCM of the same two numbers. We know that HCF of A and B when multiplied by LCM of the same numbers A and B gives us the product of the same two numbers A and B. Now we are given two numbers 306 and 657. We are given that HCF of these numbers is 9. So it's very easy for us to find the LCM, which will be found by using this equation where it says that HCF multiplied by LCM is equal to the product of two numbers. So in our case, LCM of the numbers 306 and 657 will be 306 multiplied by 657 divided by the HCF of these two numbers, which will be equal to 201,042 divided by 9, which will be 22,338. Hence, we can say that the LCM of 306 and 657 is equal to 22,338 as our answer. Let's now solve the question number 5, which says check whether 6 raised to power n can end with the digit 0 for any natural number n. So we know that if the number 6 raised to power n were to end with the digit 0, then it would be divisible by 10. We also know that 10 can be prime factorized as 2 multiplied by 5. That is, the number 6 raised to power n, if it were to end with the digit 0, then it would be divisible by 5 and 2. In other words, prime factorization of 6 raised to power n would contain prime numbers 5 and 2 if 6 raised to power n were to end with the digit 0. And let's call this as our statement number 1. Let's see also that 6 raised to power n is equal to 2 multiplied by 3 whole raised to power n, which is equal to 2 raised to power n multiplied by 3 raised to power n, which gives us that the prime factors of 6 raised to power n are 2 raised to power n and 3 raised to power n. And let's call this as our statement number 2. From statement number 2, we see that the prime factors of 6 raised to power n do not include the prime number 5. But in order to end with the digit 0, the prime factorization of 6 raised to power n must contain number 5. And this is what we have found from our statement number 1. So we can clearly say that 6 raised to power n cannot end with the digit 0 for any natural number n. Hi, this session is on Mathematics, Chapter 1, Real Numbers for Grade 10. Exercise 1.2, question number 6. Question number 6 says, explain why this expression and this expression are composite numbers. So let's solve this expression number 1 first. So the given expression is equal to 7 times 11 times 13 plus 13. Let's take 13 as a common factor and we will get the given expression to be equal to 13 times 7 times 11 plus 1. Note that we have kept a bracket here. Now let's solve inside of the bracket and then we shall get that this given expression is equal to 13 times 78. We can further decompose this expression as 13 times 2 times 3. Or we can write it as 2 multiplied by 3 multiplied by 13 raised to power 2. Now from this equation, or that the given expression is equal to 2 times 3 times 13 square, we observe that the given expression has at least 3 factors, which is 2, 3 and 13, or you can say that there are more than 2 factors of this given expression. Now by definition of a prime number, we know that a prime number always has 2 factors. First factor is the number 1 and the second factor is the number itself. So if this given expression, that is this given expression, were to be a prime, it would contain only 2 factors. But here we are saying that this given expression has more than 2 factors. Therefore, we can simply say that the given expression is not a prime number. And if it is not a prime number, then it will be a composite number, because if a number is not prime, it will be a composite number, and hence we have explained why the given expression in the question is a composite number. Let's do the solution for the part 2, or the expression number 2. This expression is 7 times 6 times 5 times 4 times 3 times 2 times 1 plus 5. So let's take number 5 as the common number, and we see that the given expression can be written as equal to as 5 times bracket start 7 times 6 times 4 times 3 times 2 plus 1. Now let's solve the inside of the bracket and we will see that this given expression can be written as 13 times 1009. So if you notice that we have actually eliminated the addition operation, that is the plus sign. So initial expression which was given to us had this plus sign, which we have now solved and eliminated it. Hence we can easily identify the factors, because if the plus sign or the addition operation were to remain in the expression, it was difficult for us to find the factors. So now that we have obtained the expression as multiplication of different numbers, we can simply say that the given expression has factors 13 and 1009. And from this equation we clearly see that the given expression has 13 and 1009 as its factors, which are more than 1, and therefore this given expression is not a prime number and hence it is a composite number. Hi, this session is on Mathematics, Chapter 1, Real Numbers for Grade 10. Exercise 1.2, question number 7. Question states, there is a circular path around the sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So before we start solving the question, there are some observations. Note that both Sonia and Ravi are moving in the same direction. Ravi is moving faster, hence he will take lesser time than Sonia to complete one round, and which we can already see that 18 minutes is taken by Sonia and Ravi takes 12 minutes. Ravi and Sonia will meet again when Ravi has completed one full extra round with respect to Sonia. And now let's see that Ravi takes 12 minutes and Sonia takes 18 minutes to complete one round. They will meet again when they hit the first common multiple of their times, that is common multiple of 12 minutes and 18 minutes. That is, if we were to find the LCM of these times taken by each of them, we will get the time when they will meet again. So let's try and find the LCM of both 12 and 18. We can write number 18 as 2 times 3 times 3. Hence, it is equal to 2 multiplied by 3 raised to power 2. Similarly, number 12 can be decomposed into 2 raised to power 2 multiplied by 3. Therefore, the LCM of the two numbers is 36. Hence, we can say that Sonia and Ravi would meet again at the starting point after 36 minutes. Hi, welcome to this session on Mathematics, Chapter 1 Real Numbers for Grade 10. We shall be doing Section 1.4 Revisiting Irrational Numbers, Theorem 1.3. Before we proceed ahead, let's take a look at this picture. This picture shows different types of numbers that we encounter in the mathematical world. Natural numbers are generally the numbers which we use for counting, like 1, 2, 3, and so on. If we add number 0 into the set of natural numbers, then that set becomes the set of whole numbers. That is, whole numbers are 0, 1, 2, 3, 4, and so on. So let's have a little bit of different perspective. If n were to represent the set of all natural numbers, then this will be a subset of whole numbers, that is w, which is 0, 1, 2, 3, and so on. Similarly, the set w of whole numbers will be a subset of set z, which will be a subset of q, which is a set of rational numbers. Q will be a subset of R, which will be a set of real numbers. And the set of real numbers will be a subset of C, which is a set of complex numbers. If you see complex numbers, they are denoted in the form of x plus iota or I multiplied by y. So when y is not equal to 0, we get numbers called as imaginary numbers. They will be in the terms of I, that is iota, for example 2i. When this term y is equal to 0, that is this term iota multiplied by y will be 0, we shall be left with the part which is called as the real numbers. Real numbers comprise of two types of numbers, irrational numbers and also the rational numbers. So this is in a nutshell how the different number types look like. Before proceeding ahead, let's recapitulate the definition of a rational number. A number is a rational number if it can be expressed in the form of p divided by q, where p and q are integers and q is not equal to 0. Irrational number is a number which is not a rational number, or in the other terms we can say that irrational number is a number that cannot be expressed in the form of p and q, where p and q are integers and q is not equal to 0. So let's take some examples of what are the rational numbers. So let's say 4. 4 is a rational number because it can be expressed in the form of 4 divided by 1, and this is similar form as p divided by q, and p and q both are integers. 1 is not equal to 0, that is q is not equal to 0. Hence this is a rational number. Similarly, 2.5 is equal to 5 divided by 2, which is a rational number. 3 by 2 is of the form p by q, where p and q, that is 3 and 2, both are integers, and hence this is a rational number, and so on. Note that the repeating and non-terminating numbers, for example 1 divided by 3, which is equal to 0.333 repeated, are also called as rational numbers. Another example would be 2 divided by 3, which is equal to 0.666, is also a rational number. On the other hand, the irrational numbers are, for example, pi, which is equal to 3.141592, and so on. You would notice that this is never repeating and never ending number, and therefore they are called as irrational numbers. By never ending, we mean that there is no end. The list or the numbers or the digits keep going on after the decimal place. Similarly, if we see under root or the square root of 2, this value is 1.4142 and so on, which is never repeating and never ending. And by never repeating, we mean that the pattern of the digits is not repeated. If we were to go back to the rational number of 1 by 3, which is 0.33333, here the digits are repeated, and you can say a pattern is repeated. But in case of pi or square root of 2, the pattern of digits is not repeated. Similarly, let's take another number, 3.01, then 001, then 0001, then 00001. So here we see a pattern that a digit 0 is being added every time, but this is not the pattern of digits being repeated, and it is also a non-terminating number. So we can say that this number, which is written here, is also a irrational number. And also in general, a square root of p is irrational when p is a prime number, or in other words, a square root of a prime number is a irrational number. Let's now talk about theorem 1.3. Theorem 1.3 says, let p be a prime number if p divides a square, then p divides a as well, where a is a positive integer. For example, if we consider two numbers 3 and 81, then the theorem says that if 3 divides 81, then 3 will also divide the number 9, because square of 9 is 9 multiplied by 9 is equal to 81, and if p, that is number 3, is dividing a square, that is 81, then it will also divide the number 9. Let's try to prove this. Let's consider that a is equal to p1 multiplied by p2 multiplied by p3 and so on up to pn, where p1, p2 and so on up to pn are the prime numbers. Then let's calculate the a square, which will be p1, p2, p3, pn, and then again the same values, that is p1, p2, p3 and up to pn. So now by using the fundamental theorem of arithmetic, we can say that p is a prime factor of a square. And again, by using the fundamental theorem of arithmetics and its uniqueness part, we can say that the prime factors of a square are p1 multiplied by p2 multiplied by p3 and so on. And then we can also say, because that's how we started off from for the proof here, that a is equal to p1, p2 and so on. So we can also say that a is equal to p1, p2, p3 and p up to pn. Therefore, we can conclude from these 2 points that p is one of the factors of a, that is p divides a where p is a prime number. Hi, and welcome to the session on Mathematics, Chapter 1, Real Numbers for Grade 10. We shall be covering Section 1.4, Revisiting Irrational Numbers, Theorem 1.4, and Example 9. Theorem 1.4 states that square root of 2 is irrational. And let's try to prove this. We will prove this theorem by using the proof by contradiction technique. So let's assume the opposite, or let's assume the contrary to what the theorem says, and let's say the square root of 2 is a rational number. Note that we have to prove that the square root of 2 is an irrational number, but we are starting with the contradictory statement stating that let square root of 2 be a rational number. So if square root of 2 is a rational number, then it can be expressed in the form of p by q, and where p and q are integers and q is not equal to 0, because we can express every rational number in form of p by q. So we have square root of 2 is equal to p by q. Now suppose p and q have a common factor other than 1. And then if we divide both the sides by that common factor, we shall get square root of 2 is equal to a by b. Note that we have assumed p and q are any integers. They are not necessarily the prime numbers. So we can divide them by some factor which is common to them, that is common to p and q. And then after dividing, we can get that square root of 2 is equal to a divided by b, where a and b are co-primes, meaning there is no other common factor among these two numbers other than 1. And in other words, we can say the highest common factor of both these numbers is 1. And then if we simplify this equation, we get b multiplied by square root of 2 is equal to a, and let's call this as our equation number 1. Now let's take square of both the sides and we solve, and we get 2b square is equal to a square, and this implies that number 2 divides a square. And we have written it here that number 2 is dividing a square, but by using the theorem 1.3, which states that a number if divides a square, then it also divides a. So we can write that number 2 divides a as well. See here, number 2 divides a square, but now we are writing number 2 divides a because of the theorem 1.3, which we can say that a is equal to 2 times c, because 2 is a factor of a, and a can be written therefore in form of 2 multiplied by some other integer, let's say c. Now we can use the value of a from our equation 1 here, and then we can get that b square is equal to 2c square. And if we see carefully this equation, we can see that 2 divides b square, or if we write using the theorem 1.3, that number 2 also divides b. So if you see these two items that we have written here, we will notice that the number 2 divides a and number 2 also divides b, that is 2 divides b and 2 divides a as well. So let's see this, that both the numbers can be divided by 2, that is both a and b can be divided by 2. Now which is contradictory to our assumption that a and b are the co-prime numbers, because here if you see we wrote that a and b cannot be further solved, or let's say they are co-primes and they have only 1 as their highest common factor. So now we have arrived at a contradiction that a and b are divisible by 2, but we had assumed them to be co-primes, that is they have no common factor other than 1. Now this contradiction has arisen because of our incorrect original assumption that square root of 2 is a rational number. Hence, we conclude that the square root of 2 is an irrational number. Now let's take an example. This is example number 9, and let's try to prove that square root of 3 is an irrational number. We shall prove this in exactly the same manner as we have proved the previous theorem, which is to say that square root of 2 is an irrational number. The steps are exactly the same, so we shall start in the same manner by assuming that the contradictory or the opposite statement. That is, let's say square root of 3 is a rational number. That is, square root of 3 is equal to p by q, because every rational number can be put in the form of p divided by q. And now let's say p and q have a common factor other than 1, because p and q are just integers, they are not the prime numbers, so we can find a common factor among them, and then we can write the square root of 3 is equal to a divided by b, such that a and b both are co-primes. That is, they cannot be further there cannot be any further or any other factor common between a and b other than 1, or their highest common factor is 1. Now solving this, we get b times square root of 3 is equal to a. Now let's call this as equation number 1. Now if we square both the sides of equation 1, we get b square multiplied by 3 is equal to a square, which implies 3b square is equal to a square. That is, number 3 can divide a square. Now if we use theorem 1.3, which says that if a number divides a square, then it will also divide the number a. Hence we can write that the number 3 divides a, because here we see number 3 divides a square. Then we use theorem 1.3 and we get that number 3 divides a, which implies that a can be written as a multiple of 3. So let's write it as a is equal to 3 multiplied by c, and if we substitute the value of a from this equation 1, if you see this equation 1, we have a is equal to b times square root of 3, and if we place that value here and then if we square both the sides, we get 3b square is equal to 9c square, which when solved gives us b square is equal to 3 times c square, which implies that 3 can divide b square. And again, using the theorem 1.3, we say that number 3 then also divides b, because 3 divides b square. Let me just make it a little clearer here. So since 3 divides b square, then using theorem 1.3, we can say number 3 also divides b. And now from this equation number 3 and the equation number 2, we get that number 3 divides both a and b, which actually is contradictory to our assumption that both a and b are the co-prime numbers here, because this is what we had assumed or we had gotten at. So that is, though both those numbers a and b have no common factor other than 1. Now this contradiction arises because of our incorrect assumption that square root of 3 is a rational number. So we can say that we have concluded that square root of 3 is an irrational number. Hi and welcome to this session on Mathematics, Chapter 1, Real Numbers for Grade 10. We shall be covering Section 1.4, Revisiting Irrational Numbers, Examples 10 and 11. Before we go ahead, remember that the sum or difference of a rational and an irrational number is always irrational. That is, a rational number plus or minus the irrational number will give us an irrational number. As an example, 5 minus square root of 3 is an irrational number. The second fact to keep in mind is this, that the product and a quotient of a non-zero rational and an irrational number is irrational. That is, a rational number multiplied by or divided by an irrational number gives us irrational number. As an example, 3 multiplied by square root of 2 is an irrational number. Now let's solve example number 10, which says show that 5 minus square root of 3 is an irrational number. Now let us assume the opposite. Let us assume that 5 minus square root of 3 is a rational number. Now if it is a rational number, then we can find co-prime numbers a and b where b is not equal to 0, and we can write this rational number as 5 minus 3 square root of 3 is equal to a divided by b. And if we rearrange this equation, we get square root of 3 is equal to 5 minus a divided by b. Now we see that both a and b are integers, and the right hand side, that is this side, 5 minus a by b, is therefore a rational number, because all the numbers in this side, that is 5 or a or b, they are all rational numbers. Therefore we can say that the right hand side of this equation number 1 is a rational number. So if the right hand side of an equation of the equation 1 is a rational number, then its left hand side, that is square root of 3, should also be a rational number, because if it is not, then the equality will not hold, because rational number on one side cannot be equal to irrational number on the other side. Therefore, if the right hand side is a rational number, then the left hand side, that is square root of 3, will have to be a rational number as well. Now this, let's call this as equation number 2, and this equation 2 actually contradicts the fact that 3 under root of 3 is an irrational number. Now we know that square root of 3 is an irrational number by our general information and by the definition of an irrational number. We know that square root of 3 is an irrational. Therefore, when we see that square root of 3 being called as rational in equation 2, this leads us to a contradiction. And we say that this contradiction has appeared because of our initial assumption, which was that 5 minus square root of 3 is a rational number. Hence, we can conclude that 5 minus square root of 3 is an irrational number. Similarly, we can solve example number 11, which says that show that 3 times square root of 2 is an irrational number. So let's start by assuming the opposite, and let's say 3 times square root of 2 is a rational number. If this is a rational number, then we can find co-prime numbers a and b where b is not equal to 0, so that 3 times square root of 2 is equal to a divided by b. Now let's rearrange this equation as square root of 2 is equal to a divided by 3b, and let's call this as equation number 1. Now if we see the right hand side of this equation 1, we see numbers a, we see number 3, we see number b, and all these three numbers, that is 3, a and b, are integers. Therefore the right hand side of this equation 1 will be a rational number, because all these three numbers, 3a, b and number a, number b and number 3 are integers. Therefore right hand side is a rational number. Now if the right hand side of an equation which is true is rational, then its left hand side should also be a rational number. That is, square root of 2 should be equal to a rational number, and let's call it as equation number 2. Now equation 2 contradicts with the general known fact that square root of 2 is an irrational number. So we can say that this contradiction, that is square root 2 is an irrational number and here it is coming out to be as square root of 2 as a rational number, this contradiction has appeared because of our initial assumption that 3 times square root of 2 is a rational number. Hence, we can conclude that 3 times square root of 2 is an irrational number. Welcome to this session on mathematics, chapter 1 on real numbers for class 10. We are doing section 1.4, revisiting irrational numbers, exercise 1.3, questions number 1 and 2. Question number 1. Prove that square root of 5 is irrational. So let's start solving this problem by assuming the opposite. That is, let's say that the square root of 5 is a rational number. So if this is a rational number, then we can find two co-prime numbers a and b such that b is not equal to 0 and square root of 5 is equal to a divided by b. If we rearrange this equation, we get 5b square is equal to a square, which implies that a square is divisible by 5 because we have 5 here and then some other value of the integer is equal to a square. So we can say that a square is divisible by 5. Now using the theorem 1.3, which says that if a number divides a square, then this number divides the number a as well. So if a square is divisible by 5, then a is also divisible by 5. So this is what we conclude here. Now let's say that if 5 can divide a, then a can be written in the terms of 5. That is, let's write a as a is equal to 5c, where c is some integer. Now if we rearrange this equation and if we use the value of a from the equation 1, that is a square is equal to 5b square, we get b square is equal to 5 times c square, which implies that b square is divisible by 5 because we have 5 as a factor of b square. Now again using theorem 1.3, we get that b is divisible by 5. So if we see these two equations that we have arrived at, that b is divisible by 5 and a is divisible by 5, we see that a and b have 5 as a common factor. But we realize that this is contrary to the fact that both a and b are co-primes, because co-primes have only one highest common factor, HCF, which is equal to number 1. So a and b having a 5 as a common factor is contrary to a and b both being co-prime numbers. Hence we cannot express square root of 5 as a divided by b. That is, we can say that square root of 5 is an irrational number. Now let's solve question number 2, which is prove that 3 plus 2 times square root of 5 is irrational. So let's start by assuming the opposite. That is, let 3 plus 2 times square root of 5 is a rational number. If this is a rational number, then we can find two co-prime numbers a and b where b is not equal to 0, such that 3 plus 2 times square root of 5 is equal to a divided by b. Now if we rearrange this, we get square root of 5 is equal to half times a by b minus 3. Now if we see this equation carefully, on the right hand side we have numbers 2, 3, a and b. All these four numbers are rational integers. So we can easily say that the right hand side of this equation, which is this, is a rational number. Now if the right hand side of an equation is rational, then the left hand side of that equation should also be rational if that equation or the equality sign has to hold true. Therefore, we can say that square root of 5 is rational. But we know that square root of 5 is actually not equal to rational. So we use our general information or general knowledge that square root of 5 is irrational, but here we are getting square root of 5 as rational. It means that our initial assumption that 3 plus 2 times square root of 5 is a rational number is false. Hence, we can conclude that 3 plus 2 times square root of 5 is an irrational number. Welcome to this session on mathematics, chapter 1 on real numbers for class 10, section 1.4, exercise 1.3, question number 3. Question number 3 says, prove that following are irrationals. Let's solve the part 1, which is 1 divided by square root of 2. And let's start by assuming the opposite. That is, let's say the 1 divided by square root of 2 is rational. So if this is a rational number, we can find two co-prime numbers a and b where b is not equal to 0 such that 1 divided by square root of 2 can be written as equal to a divided by b. If we rearrange it, we get square root of 2 is equal to b divided by a. Now because a and b are both rational, so the right hand side of this equation will be a rational number. Also, if the right hand side of this equation is a rational number, then the left hand side should also be a rational number. Therefore, we can say that square root of 2 is equal to rational. But this is not true because we know that square root of 2 is an irrational number. Hence, we have arrived at a contradiction. So we can say that our initial assumption that 1 divided by square root of 2 is rational number is false. Hence, we conclude that 1 divided by square root of 2 is an irrational number. Let's now solve the part 2, that is 7 times square root of 5. And let's start by assuming the opposite. So let's say that 7 times square root of 5 is rational. So if this is rational, we can find co-prime numbers a and b where b is not equal to 0 such that 7 times square root of 5 is equal to a divided by b, which implies we can say that square root of 5 is equal to a divided by 7 times b. Now on the right hand side we have numbers 7, a and b which are all rational. Therefore, we can say that the right hand side of this equation is a rational number. So if in this equation, if the right hand side is a rational number, then the left hand side should also be a rational number. Therefore, we say that square root of 5 is equal to rational. But this is not true because we know that square root of 5 is actually an irrational number. Therefore, we have arrived at a contradiction. So we can say that our initial assumption that 7 times square root of 5 is a rational number is not true. Therefore, we conclude that the 7 times square root of 5 is an irrational number. Let's now solve the part number 3, which is 6 plus square root of 2. And let's start by assuming the opposite, that 6 plus square root of 2 is rational. Therefore, that is when this is a rational number, we can find co-prime numbers a and b where b is not equal to 0 such that 6 plus square root of 2 is equal to a divided by b. And if we rearrange it, we get square root of 2 is equal to a plus a divided by b minus 6. And if we see the right hand side of this equation, we see that this right hand side of the equation is a rational number because all the numbers on this side, that is 6, A and B, are rational. So if the right hand side of this equation is a rational number, then the left hand side of the equation should also be a rational number. That is, we can say this left hand side here is square root of 2 is equal to rational number. So we get from this arrangement, and by assuming this whole given equation to be a rational number, that square root of 2 is a rational number, which is not true, because square root of 2 is actually an irrational number. Hence, our initial assumption that 6 plus square root of 2 is a rational number is false. Therefore, we conclude that 6 plus square root of 2 is an irrational number. Hi, welcome to this session on mathematics, chapter 1, real numbers, for grade 10, section 1.5, revisiting rational numbers and their decimal expansions, theorem 1.5 and 1.6. But before we proceed ahead, remember that a rational number can have either a terminating decimal expansion or a non-terminating but repeating decimal expansion. Example would be, for the terminating decimal expansion would be 5 divided by 2, which is equal to 2.5, and the example for non-terminating and repeating example would be 1 by 3, which is equal to 0.333, and so on. For the first part, which is a terminating decimal expansion, we have theorems 1.5 and 1.6, and for the second point, for that is non-terminating but repeating, we have theorem 1.7. So what do these theorems say? So theorem 1.5 states that let x be a rational number whose decimal expansion terminates. So this is an important word here. Then x can be expressed in the form of p divided by q, where p and q are co-primes, and prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are both non-negative integers. And theorem 1.6 states that let x be equal to p by q, a rational number, such that the prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. So now let's take some examples which pertain to theorem 1.5. Let's consider 0.375, which is equal to 375 divided by 1000, which can be factorized and can be written as 3 multiplied by 5 raised to power 3 divided by 2 raised to power 3 and 5 raised to power 3. Now we can cancel out the common ones. 5 raised to power 3 goes out, and we are left with 3 divided by 2 raised to power 3. Similarly, 0.104 is equal to 104 divided by 1000, which can be written as 13 multiplied by 2 raised to power 3 divided by 2 raised to power 3 multiplied by 5 raised to power 3. And now we cancel out the common factors. In this case it is 2 raised to power 3 and 2 raised to power 3 goes out here, and we are left with 13 divided by 5 raised to power 3. Similarly, 0.0875 is equal to 875 divided by 10,000, which can be written as 875 divided by 10 raised to power 4, which is equal to 5 raised to power 3 multiplied by 7 divided by 2 raised to power 4 multiplied by 5 raised to power 4. And then we will be left with, after cancelling the common factors here, we are left with 7 divided by 2 raised to power 4 multiplied by 5. And now let's take another example. 23.3408 can be written as 233408 divided by 10 raised to power 4, which can be written as 2 raised to power 6 multiplied by 7 multiplied by 521 divided by 2 raised to power 4 multiplied by 5 raised to power 4. Cancelling out the common factors, we shall be left with 2 raised to power 2 multiplied by 7 multiplied by 5 raised 521 divided by 5 raised to power 4. Now if you see here carefully in this box and this box, we can say that for any real number which has a decimal expansion that terminates, that number can be expressed as a rational number whose denominator is of the power of 10. So if you see here, we have converted all of them into the denominator with a power of 10. We know that only prime factors of 10 are 2 and 5. Hence, by cancelling the common factors in the numerator and denominator, we can say that the real number can be expressed in the form of p divided by q, where prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m. And if we were to state this more formally, we can write the theorem 1.5 again, and I'll repeat it here. That theorem 1.5 states that let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p divided by q, where p and q are co-prime numbers, and the prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are non-negative integers. Now let's take a few more examples for theorem 1.6. Let's take 3 divided by 8, which is equal to 3 divided by 2 raised to power 3. And now we convert the denominator into the power of 10 by multiplying and dividing by 5 raised to power 3 here. And we get 375 divided by 1000, which is equal to 0.375. Similarly, let's take 13 divided by 125, which is equal to 13 divided by 5 raised to power 3. And if we convert the denominator, which is this here, into the power of 10, we get 2 raised to power 3 multiplied by 13 whole divided by 2 raised to power 3 into 5 raised to power 3, which is equal to 104 divided by 1000, which is equal to 0.104. Now another example is 7 divided by 80. We can write it as 875 divided by 10 raised to power 4, which is equal to 0.0875. And the final example for now is 14588 divided by 625 is equal to 2 raised to power 2 multiplied by 7 multiplied by 521 whole divided by 5 raised to power 4. And if we convert the denominator, this is the denominator, into the power of 10, we get 233408 divided by 10 raised to power 4, which is equal to 23.3408. And now let's focus on the values which are in this box here. They are all having a denominator in the power of 10. So it appears that we can convert a given rational number of the form p divided by q, where q is of the form 2 raised to power n multiplied by 5 raised to power m, to an equivalent rational number of the form a divided by 10 raised to power c, that is a denominator is having some power of 10. And more formally, if we state, we will arrive at the theorem 1.6's text, which states that let x be equal to p divided by q be a rational number such that the prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are non-negative integers. Then x has the decimal expansion which terminates. So this is the important thing, that x has the decimal expansion which terminates. Welcome to this session on Mathematics, Chapter 1 on Real Numbers for Class 10th. Here we shall cover Section 1.5, Revisiting Rational Numbers and Their Decimal Expansions, Theorem 1.7. Before we proceed ahead, remember that rational numbers have either a terminating decimal expansion or a non-terminating repeating decimal expansion. Example of a terminating decimal expansion is 5 divided by 2, which is equal to 2.5. It terminates, and it is a terminating decimal expansion. Example of non-terminating and repeating is 1 divided by 3, which is equal to 0.1 3, 3, 3, and so on. It is a non-terminating and repeating decimal expansion. For the terminating decimal expansions, we have theorems 1.5 and 1.6, and for non-terminating repeating decimal expansions, we have theorem 1.7. Let's see 1 divided by 7. This is equal to 0.142857. Again, the numbers are repeated: 142857, 142857, and so on. Notice that in 1 divided by 7, the denominator 7 is not of the form 2 raised to power n multiplied by 5 raised to power m, and that 1 by 7 will not have a terminating decimal expansion, because you see here it is non-terminating. That is, the remainder of the blocks, which is a remainder, and the blocks of digits in the quotient, which is this, will keep repeating. And as we have already seen that 1 by 7 is equal to 142857, then again repetition of 142857, and so on. And we can say that there will be a non-terminating decimal expansion for 1 by 7, which is having a denominator of 7, which is not of the form 2 raised to power n, 5 raised to power m. And this fact is true for all the rational numbers which are not covered under the theorems 1.5 and 1.6, which we have covered in a previous session. But what do 1.5 and 1.6 cover? They cover all the rational numbers which are of the form p divided by q, where q's prime factors are of the form 2 raised to power n multiplied by 5 raised to power m. But here we are covering the denominators which are not in the form of 2 raised to power n and 5 raised to power m. So you can now formally state this in a form of a theorem that let x be a rational number of the form x is equal to p divided by q, where p and q are the co-primes, that is, they are co-prime numbers, such that the prime factorization of q is not of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating repeating format. So this is theorem 1.7. Also, let's see that from theorems 1.5, 1.6 and 1.7, we can say that the decimal expansion of every rational number is either terminating or non-terminating repeating expansion. Let me repeat it here. The decimal expansion of every rational number is either terminating or a non-terminating expansion. Welcome to this session on mathematics, chapter 1, real numbers, for class 10. We are covering section 1.5, revisiting rational numbers and their decimal expansions, exercise 1.4, question number 1. Question number 1 states, without actually performing the long division, state whether the following rational numbers will be having a terminating decimal expansion or a non-terminating repeating decimal expansion. And the numbers given to us are these. Before we start solving the question, remember that if the denominator of the given number is of the form 2 raised to power n multiplied by 5 raised to power m, then the decimal expansion of the given number is terminating. But if the denominator of the given number is not of the form 2 raised to power n multiplied by 5 raised to power m, then the decimal expansion of the given number is non-terminating repeating type. So question number 1, part 1, 3 divided by 3125, and let's focus only on its denominator, which is 3125, which can be factorized in the 5 multiplied by 5 multiplied by 5 multiplied by 5 and so on, that is 5 raised to power 5. And this denominator is of the form 2 raised to power n multiplied by 5 raised to power m, where n is equal to 0 and m is equal to 5, and hence we can say that the decimal expansion of the given number is terminating. The answer to 1, 2, that is the second number, is let's focus only on its denominator, which is 8, which can be expressed as 2 multiplied by 2 multiplied by 2, that is 2 raised to power 3, which is of the form 2 raised to power n multiplied by 5 raised to power n, and therefore we can say that the decimal expansion of the given number, which is 17 by 8, is terminating. The part 3 of the question, the number given to us is 64 divided by 455, and let's focus on its denominator and factorize it, and we get 455 is equal to 4 multiplied by 7 multiplied by 13, which is equal to 2 raised to power 2 multiplied by 7 multiplied by 13, and this is not of the form 2 raised to power n multiplied by 5 raised to power m, because it is also having 7 and 13, and therefore we can say that the denominator is not of the form 2 raised to power n multiplied by 5 raised to power m. Therefore it is non-terminating repeating decimal expansion. Answer to first part 4. The number given is 15 divided by 1600, and the 1600 is the denominator, which can be expressed as the as 2 multiplied by 2 up to 6 times, multiplied by 5 and then multiplied by 5, which is 2 raised to power 6 multiplied by 5 raised to power 2, and this is of the form 2 raised to power n multiplied by 5 raised to power m, and hence we can say that the decimal expansion of the given number 15 divided by 1600 is terminating. Answer 1-5. The given number is 29 divided by 343. The denominator is 343, which is equal to 7 multiplied by 7 multiplied by 7, which is equal to 7 raised to power 3, which is not of the form 2 raised to power n 5 raised to power m, because it contains powers of 7, and therefore we can say that the decimal expansion of the given number, which is 29 divided by 343, is non-terminating repeating type. Answer 1-6. The given number is 23 divided by 2 raised to power 3 multiplied by 5 raised to power 2, and we notice that the denominator is of the form 2 raised to power n 5 raised to power m, where n is equal to 3 and m is equal to 2. Therefore we can say that the decimal expansion of the given number is of the terminating type. Answer to part 7 of the question number 1. The given number is 129 divided by 2 raised to power 2, 5 raised to power 7, and then 7 raised to power 5. And the denominator is definitely not of the type 2 raised to power n, 5 raised to power m, because it contains powers of 7. And therefore we can say that the decimal expansion of the given number is of the non-terminating repeating type. Question 1, part 8. Given number is 6 divided by 15. We have 6 divided by 15 is equal to 6 divided by 5 multiplied by 3, and then we can write it also as 2 multiplied by 3 divided by 5 multiplied by 3, which is equal to 2 divided by 5. And if we focus only on the denominator, which is 5, of the format of 2 raised to power n 5 raised to power m, where n is equal to 0 and m is equal to 1. Therefore we can say that the decimal expansion of the given number 6 divided by 15 is terminating. Let's see the part 9 of question number 1. The given number to us is 35 divided by 50, which can be written as 5 multiplied by 7 divided by 2 multiplied by 5 multiplied by 5, which is equal to 7 divided by 10. And let's see the denominator of it. And if we factorize that, we get 2 raised to power 1 multiplied by 5 raised to power 1, which is of the form 2 raised to power n multiplied by 5 raised to power m, whereas n is 1 and m is also 1. Therefore we can say that the decimal expansion of the given number 35 by 50 is a terminating one. And if you notice this given number, we can easily solve it in another manner by writing 35 divided by 50 is equal to 35 multiplied by 2 divided by 50 multiplied by 2. What we have done here is that we have multiplied and divided the number by 2, and we got 70 divided by 100. And if you notice the denominator, it is of the form 2 multiplied by 5 whole raised to power 2, which is equal to 2 raised to power 2 multiplied by 5 raised to power 2, which is of the form 2 raised to power n multiplied by 5 raised to power m. So we can say that the decimal expansion of the given number is terminating. And let's see the last part of question number 1, which is 110, which is 77 divided by 210. and if we focus only on the denominator, we see this is 210, which is equal to 7 multiplied by 3 multiplied by 10, which is equal to 7 multiplied by 3 multiplied by 2 multiplied by 5, and this is not of the form 2 raised to power n and 5 raised to power m, because it contains powers of 7 and 3. Therefore, we can say that the decimal expansion of the given number 77 divided by 210 is non-terminating repeating. Hi, welcome to this session on Mathematics, Chapter 1, Real Numbers for Class 10, Grade 10. In this session, we are covering Section 1.5, Revisiting Rational Numbers and Their Decimal Expansions, Exercise 1.4, Question number 2. The question number 2 states, write down the decimal expansions for those rational numbers in question 1 which have terminating decimal expansions. That is, write the decimal expansions for these numbers, the numbers which are not crossed out here. Note that to find the decimal expansion, we shall try to convert the denominator of the given number into the power of 10, because it will make it easier for us to convert the given number into the decimal expansion. So answer to the part 1 is that we are given 13 divided by 3125 as the given number, and which is equal to 13 divided by 5 raised to power 5. And now we multiply and divide this given number by 2 raised to power 5. And we get 13 multiplied by 32 divided by 2 raised to power 5 multiplied by 5 raised to power 5, which is equal to 416 divided by 10 raised to power 5, and that can be written as 0.00416, and that is the decimal expansion, and that's our answer. The part 2 is that the given number is 17 divided by 8, and this number can be written as 17 divided by 2 raised to power 3. We multiply and divide this number by 5 raised to power 3, and we get 17 multiplied by 125 divided by 2 multiplied by 5 whole raised to power 3, and that is equal to 2125 divided by 1000, which is equal to 2.125, and that is the required decimal expansion that we are looking for. Answer to part 4. The given number is 15 divided by 1600, which can be written as 15 divided by 2 raised to power 6 multiplied by 5 raised to power 2, and now we multiply and divide this number by 5 raised to power 4, and we get 15 multiplied by 625 divided by 2 into 5 whole raised to power 6, which is equal to 9375 divided by 10 raised to power 6, and that is equal to 0.009375, and that is the decimal expansion we are looking for. The answer to part 6, the given number is 23 divided by 2 raised to power 3 multiplied by 5 raised to power 2, and that is equal to 23 divided by 2 raised to power 3 multiplied by 5 raised to power 2. We multiply and divide this given number by 5, and we get 23 multiplied by 5 divided by 2 into 5 whole raised to power 3, which is equal to 115 divided by 1000, which is equal to 0.115, and that is the answer or the decimal expansion we are looking for. Answer to part 7, the given number is 6 divided by 15, which is equal to 2 divided by 5, and we now multiply and divide this given number by 2. We get 4 divided by 10, which is equal to 0.4, which is our required decimal expansion. The answer to part 9 of 2, the question number 2, is that we are given the number 35 divided by 50, and we multiply this given number by 2. We get 35 into 2 divided by 100, which is equal to 70 divided by 100, which is equal to 0.07, and that is the required decimal expansion. Welcome to this session on Mathematics, Chapter 1, Real Numbers for Class 10. We are covering Section 1.5, Revisiting Rational Numbers and Their Decimal Expansions, Exercise 1.4, Question number 3. Question number 3 says, the following real numbers have decimal expansions as given below. in each case decide whether they are rational or not. If they are rational and of the form P divided by Q, what can you say about the prime factors of Q? So answer 3, 1. The given number is 4, 3.123456789. So we notice that the given number has a terminating decimal expansion, because it is, if you see this decimal expansion, it is not going beyond 1, 2, 3, 4, 5, 6, 7, 8, 9. And therefore, using what we have our knowledge about the rational numbers, we can say that the given number is a rational number. Now using theorem 1.5, because we can use the theorem 1.5 because the given number is a rational number and it has a terminating decimal expansion. So we can say using the theorem that this given rational number can be expressed in the form of P divided by Q, such that P and Q are co-primes and the prime factorization of Q is of the form 2 raised to power n multiplied by 5 raised to power m. So what can we say about the prime factors of Q, as is asked in the question, is that we can say that the prime factors of Q will be either 2 or 5 or both. Now let's tackle the part 2. The given number is 0.120, 1200, 12000 and 1200000. So we notice that this is a non-terminating decimal expansion, and also we notice that this is non-repeating, because this pattern, let's say 120, is not repeated because then there is a 0 added here also. So this is not the given number is not a rational number, so we are not going to worry about it and we are not going to comment about its Q and its prime factors. Answer 3, part 3. The given number is 43.123456789, 123456789, 123456789 and so on. We are repeating the digits from 1 to 9 because there is a bar over them. So this bar implies that these numbers are repeated. So we notice that this is a non-terminating decimal expansion, and also it has a recurring pattern of 1, 2, 3, 4, 5, 6, 7, 8, 9, which is again repeated 1, 2, 3, 4, 5, 6, 7, 8, 9 and so on. So using the easy thing that we know about the rational numbers, we can say that the given number is a rational number because it has a non-terminating recurring pattern. So now inferring from theorem 1.7, we can say that this rational number can be expressed in the form of P divided by Q, such that Q is not of the form 2 raised to power n multiplied by 5 raised to power m. So what can we say about the prime factors of Q, as is asked in the question, is that the prime factors of Q will also have a factor other than 2 or 5, because we notice that Q is not of the form 2 raised to power n multiplied by 5 raised to power m. Hi, welcome to this session on Mathematics, Chapter 1, Real Numbers for Grade 10. We are covering relationship between HCF and LCM of 2 numbers and 3 numbers. In previous sessions, we have already talked in detail about the HCF and LCM, and we have also done some examples related to the HCF and LCM of 2 numbers and relationship between them. So here we just summarize by saying that the HCF of 2 numbers A and B, when multiplied by the LCM of the same 2 numbers A and B, gives us the product of those 2 numbers. So in summary, we can say that the HCF of AB multiplied by LCM of AB is equal to product of A and B. But this is valid only for 2 numbers. So what happens if we have 3 numbers A, B and C? In that situation, the HCF multiplied by LCM is not equal to the product of those 3 numbers A, B and C. So in that situation, we have different equality which holds. So let's say there are 3 numbers that we have A, B and C. In that scenario, HCF of 3 numbers, that is HCF of A, B, C, will be equal to A multiplied by B multiplied by C, then whole multiplied by LCM of A, B and C divided by LCM of AB multiplied by LCM of BC multiplied by LCM of
AC. Similarly, if we have to get the LCM of A, B and C, we will have LCM of A, B and C is equal to A multiplied by B multiplied by C multiplied by HCF of three numbers A, B, C, and then divided by HCF of AB multiplied by HCF of BC multiplied by HCF of AC.